today's sections, we are going to look about Raoults Law. Let's start with liquid in liquid solutions. Liquid in liquid solutions contains solute as well as solvent in liquid form. Then mixability. So mixability is the property of two substances to mix in all proportions. They fully dissolve at any concentration. Example, alcohol and water. Alcohol and water mix in all proportions. Liquids are said to be immiscible if they do not form a homogeneous solution in certain proportions. Example, oil in water. So based on the mixability, liquid in liquid solutions are classified into three types. Completely mixable liquids, example, alcohol and water. Partially mixable liquids, example, phenol and water. So partially mixable liquids will have their mixability depend on temperature. So mixability of partially mixable liquids depend on temperature. And completely immiscible liquids, example, oil and water. Completely mixable liquids. Ideal solutions. So ideal solutions are homogeneous solutions in which the intermolecular forces are same. That means the force of attraction between a solute and another solute, or the force of attraction between a solvent and another solvent, will be equal to the force of attraction between a solute and solvent, right? To make it very simple, the force of attraction between like molecules will be equal to the force of attraction between unlike molecules. In that case, that particular solution behaves as ideal solution. In order to form an ideal solution, we need to have the solute and solvent to be very similar in their molecular structure and size. An ideal solution will have physical properties which are closely related to its pure components. The important characteristic feature of ideal solution is ideal solutions will have zero enthalpy of mixing, which means when ideal solution is formed, there is no change in the heat. There will be no change in the enthalpy. Okay, enthalpy of mixing is change in the heat energy when a solute is dissolved in a solvent. So how does it happen? How enthalpy of mixing of a ideal solution is zero? This is due to the fact that the intermolecular force of attraction between like molecules is equal to the intermolecular force of attraction between unlike molecules. Since they are equal, the enthalpy of mixing is zero. In other words, whenever a bond is broken, it requires energy. Likewise, whenever a new bond is formed, it releases energy. Now, in this ideal solution, the energy which is required to break the bond is equal to the energy which is released when a new bond is formed. Therefore, it doesn't show any change in the heat energy when a solute and solvent is mixed, right? So the attractive forces are equal. Therefore, no heat is evolved or absorbed when ideal solutions are formed. If there is any change in the temperature while forming a solution, then that solution will not be an ideal solution. Example for ideal mixtures: hexane and heptane, propane 1-ol and propane 2-ol, benzene and methyl benzene. So you can observe here they are similar: hexane, heptane, benzene and methyl substituted benzene. So it is confirmed that the solute as well as the solvent should be similar in their molecular structure and chemical structure, then only they can produce an ideal solution, right? Now let us consider liquid A. This is liquid A having so many molecules, and few molecules of liquid A is having more energy than other molecule. Due to that excess energy, it is trying to convert into a gaseous form, right? So those and molecules which is having more energy than other molecules is now trying to convert into a gaseous form. The escaping tendency of that molecules, for example, here it is 4 molecules, right? So we have another solvent B, which is similar to A. So that means at any particular temperature, the solvent B also will be look like solvent A. So here this is solvent B or liquid B. So it's having same number of molecules, almost same. And as I said, it is having similar characters and similar intermolecular forces. So here also we have 4 molecules which is possessing excess energy and trying to escape and convert into a gas, right? So when liquid A and liquid B is mixed in 50-50 ratio, right, it produces a ideal solution. So you can see here now same 100 molecules is there. Now this 100 molecules is made up of 50 molecules of A and 50 molecules of B. Another important and interesting fact to be noted is after mixing A and B also, the number of molecules trying to escape is 4 only. In that 2 belongs to A and 2 belongs to B. So this will happen only for ideal solutions. And the reason for that is the forces of attraction between liquid molecules A and the force of attraction between liquid molecules B is equal to the force of attraction between liquid A and liquid B molecules. So that is the important and striking factor to observe in an ideal solution. Raoults law. So ideal solutions will obey Raoults law. So according to Raoults law, the partial vapor pressure of a component in a mixture is equal to the vapor pressure of the pure component at that temperature multiplied by its mole fraction. So the Raoults law is useful to know the partial vapor pressure of the component, okay, after mixing into an ideal solution, which is given as product of concentration of the component multiplied by vapor pressure of the pure component. So let us apply the same thing in this example. So vapor pressure exerted by pure liquid A is P A naught, and vapor pressure exerted by the pure liquid B is P B naught, right? Then the concentration of A in the solution is given as mole fraction of A XA. The concentration of B in the solution is given as XB. So XA and XB denotes mole fraction of the solute and mole fraction of the solvent. Now applying the Raoults law, the partial vapor pressure of any component A or B is given as vapor pressure of the pure component multiplied by mole fraction of the component, right? In that case, partial vapor pressure of component A is given as P A naught multiplied by XA. Likewise, partial vapor pressure of component B is given as P B naught into XB, right? So ideal solutions obey this Raoults law. Since it is obeying Raoults law, we can compare these ideal solutions into a gas. So we know that the mixture of gas is given by Dalton's law of partial pressures. So according to Dalton's law of partial pressure, the total pressure exert after mixing the gases. So after mixing the gases, the total pressure exerted by the individual component is equal to the total pressure of the gas is equal to the sum of partial pressure of the gases in the mixture, right? So the Dalton's law of partial pressure applicable for the gas can also be applicable to these ideal liquid solutions. So according to that, total pressure of the solution. Now we are replacing the gases term by the term solution. Okay, so total vapor pressure of the solution is nothing but sum of partial vapor pressure of the component A and partial vapor pressure of the component B. So we are just replacing the term gases with the word solution because ideal solutions are behaving like gas. Now, by using this Dalton's law of partial pressures, it is now possible for us to calculate the vapor pressure of the ideal solution after mixing the components. It is given as vapor pressure P equals to partial vapor pressure of A and partial vapor pressure of B, which is already derived by Raoults law. So the final equation will be P equals PA naught into XA plus PB naught into XB, where PA naught is the vapor pressure of individual pure component and XA is the concentration of the component A, right? So when you are going to mix n number of components, you can just add with those components C, D, E, F like that, right? Then expression of Raoults law. So Raoults law can be expressed in a vapor pressure composition curve. Okay, so this is a vapor pressure component composition curve where y-axis denotes the vapor pressure and x-axis denotes the concentration of the component. Okay, so the x-axis is now given in a mole fraction. So when you travel towards the right hand side, you can see that the concentration of the component A is increasing. So these are the different solutions with different compositions. So the first solution here contains 0 mole fraction of A. That means the total component is made up of total solution is made up of component B. Okay, so when you travel towards the right hand side, you can see there the concentration of A starts to increase and the component B starts to decrease, right? So this line, this red line denotes the partial vapor pressure of component A. So partial vapor pressure of component A, PA equals to PA naught into XA. So this PA naught into XA is represented by this line. Okay. Likewise, the partial vapor pressure component of B is plotted. So here you can see here now, this is the first solution containing 0 mole fraction of A and all made up of B, right? So as we move towards right hand side, the component A increases and the component B decreases. So initially, the whole solution is made up of only B. So the vapor pressure is totally contributed by the B component. So the point starts from here. As we move on to the right hand side, the concentration of B decreases. So you get a negative slope, right? So the green line denotes the partial vapor pressure of component B, right? And this red line denotes partial vapor pressure of the component A, right? Now this is now extrapolated into applying the Dalton's pressure. So Dalton's law of partial pressure, and applying this law, this dark blue line denotes total vapor pressure of the mixture after mixing A and B, right? So total vapor pressure nothing but sum of partial vapor pressure of component A denoted by red line and partial vapor pressure of the component B denoted by green line. So these 2 points are connected, which means they both are added. So this is the vapor pressure curve for Raoults law, right? So any solution which gives a curve like this denotes they are ideal solutions. So if the lines are straight lines, then we say that they obey Raoults law. Any solution which obeys Raoults law are called as ideal solutions, right? Example, heptane, hexane, then benzene, methyl, benzene. It is observed that not all solutions follows Raoults law. There are deviations observed from Raoults law. Okay, so this vapor pressure composition curve denotes a positive deviation from Raoults law. You can see here now they are not having straight lines, they are curved. The dotted lines denoted expected response. I mean, these are the dotted lines denotes the ideal lines. Whereas in practical observation, it is not showing a straight line, it is all curved. So when the graph shows a curve, we say that it is deviated from Raoults law. This particular deviation is known as positive deviation. So when positive deviation occurs? When the total vapor pressure is greater than sum of partial pressures of individual components. According to the Dalton's law, total vapor pressure is equal to sum of partial pressure. Deviations, when deviation happens, they are not equal, they are greater. Okay, when they are greater, then positive deviation takes place. When and why it is greater, right? That is due to cohesive force of attraction is greater than the adhesive force of attraction. Whenever the cohesive force attraction is greater than adhesive force of attraction, positive deviation occurs. The factors which leads to increase in cohesive force are difference in polarity between solute and solvent, length of the hydrocarbon chains of solute and solvent, and degree of association. Due to these factors, the cohesive force of attraction increases, thereby the total vapor pressure is more than the sum of partial pressures of individual component. The example of solution demonstrating positive deviations are carbon tetrachloride and cyclohexane. Right? Likewise, negative deviations are also observed from Raoults law. So negative deviation happens when total vapor pressure is less than the sum of partial pressure of individual components. So you can see the curve here. Dotted lines is the ideal solution, and you can see the curves are below the ideal line. Example for the solutions showing negative deviation is chloroform and acetone, and the factor which is causing this is decrease in the cohesive force. Okay, the cohesive force is less than the adhesive force, so the adhesive force is more. The reason for increase in adhesive force are hydrogen bonding, salt formation, and hydration. Because of these factors, the adhesive force increases, thereby the total vapor pressure is less than the sum of partial pressure of individual components. So non-ideal solutions shows either positive deviation or negative deviation, right? And I hope and believe that you are all benefited with some important points related to Raoult's law. And thank you for joining in this class. I hope to see your inputs in comments, and bye for now. Thank you.